Okay, then I think it's time to start this session. So welcome everyone to this invited talk session at QCrypt. Today we are joined by Professor Bing Chi from Oak Ridge National Laboratory to talk about discrete variable QKD using conjugate homodyne detection. So I think this is a talk that's probably going to challenge a bit the way we think about discrete variables and continuous variable protocols, and ask, can you use the measurements from continuous variables in discrete variables? So I'm sure the session is going to generate many questions from the community, and of course encourage to ask them in the chat channel. I will then read them out at the end, and you can also use the raise your hand button. So now I yield the floor to our speaker.
Thanks, Thomas. So let me share my screen first. Is that looks okay?
Yes, it does.
Okay, that's great. And good morning, good afternoon, and good evening. So first, I'd like to thank the organizer for inviting me to give a talk. Wait a minute. Okay, now it's okay. Today I'm going to present our recent work of doing discrete variable quantum key distribution using conjugate optical homodyne detector. Now, the most part of my talk is a brief summary of these two following papers. And in the first work, my collaborator and I developed a scheme of using two optical homodyne detectors to determine the photon number distribution of an unknown quantum state. And in the second paper, we applied this detection scheme in the BB84 QKD protocol. So the two detection schemes have been applied in QKD. One is single photon detection, and the other one is optical homodyne detection. And this is actually similar to the case in classical optical communication, where we have direct detection scheme and a coherent detection scheme. And single photon detectors have been widely used in discrete variable DVQKD. And in analog to the direct detection scheme in classical optical communication, the output of a single photon detector is insensitive to the phase of the input optical signal. And so most of the SPD used in QKD operate in this threshold mode, where so it can distinguish vacuum state from non-vacuum state, but normally it cannot resolve photon numbers. So due to the required very high detection efficiency, the single photon detector for QKD is quite different from the direct detection scheme in classical optical communication, and dedicated devices have been developed over the years. And today's state-of-the-art SPD can give us both good detection efficiency and a very low dark counter rate. And this is crucial for doing QKD over a long distance. But nevertheless, there are some limitations of single photon detector besides they are expensive. So most of them are operated at a very low temperature, and it will be a challenge if we want to integrate the whole system on a single chip. And most single photon detector have take time, which means once they detect a photon, they need some time to recover before they can detect another photon. And this might not be a big problem for long distance QKD, but for short distance application, this may eventually limit how fast you can operate this system. Now, optical homodyne detectors has been applied in both continuous variable QKD and the classical coherent communication. And they are actually very similar. So some state-of-the-art classical receiver, they can be operated at the short noise regime, which means they are qualified for quantum applications. So in let me move this a little bit somewhere. Okay. So in coherent detection, we have typically a very strong local oscillator to interfere with the weak quantum signal at a beam splitter. And the resulting interference signal is typically strong enough and can be detected with room temperature photodiodes. And because these two signals are highly unbalanced, and in order to move the DC background, so normally we use the balance detection scheme. So this detection scheme has been well developed and is highly efficient, and it can be operated at high speed because essentially it has no dead time. And furthermore, the strong local oscillator is also function as a very well filter. So this makes this detection scheme is appealing in certain applications when you want to do QKD over a channel with broadband noise photons. For example, you want to do coexistence of QKD with classical communication signals through the same fiber. So nevertheless, there is a technical challenge in a coherent detection. That is, we need a phase reference between the transmitter and the receiver. So in CVQKD, so two different schemes has been developed. So the first scheme, the conventional scheme, is we could generate both the local oscillator and the quantum signal from the same laser at farthest end and send both of them through the same fiber to the receiver. And another recent scheme is to generate the local oscillator really locally at the box end. And in order to recover the optical phase, so artists can send some phase reference signals. And both of these schemes have been demonstrated over practical distance, and they really work in practice. But nevertheless, they will introduce some additional complexities of your system. So the motivation of our work is really convey operate optical homodyne detector, which is typically used in CV quantum communication, and convey operate that in a phase insensitive photon counting mode to implement DVQKD. And such a scheme may inherit certain advantages of coherent detection without requiring a phase reference between Alice and bulb. And this could be a simpler solution than the existing QKD protocols. So let me start from the basic idea of using a conjugate homodyne detector to do photon counting. So in classical EM theory, we know an arbitrary electrical field can be written as a sum of a cosine term and a sine term. And the energy is proportional to EX squared plus EP squared. So now in quantum optics, these two components are corresponding to two field quadratures. And these two field quadrature can be measured using two optical homodyne detectors. So we could expect by a calculate X squared plus P squared, we can have some information on the photon number of the input quantum state. So this sounds promising, but we also know X and P are not commute with each other. And this suggests from the uncertainty principle, this measurement scheme is intrinsically noisy. And now the question is how noisy it is and whether we can still apply that to do QKD. So the basic structure of a conjugate homodyne detector is shown in this diagram. So we have a quantum state input and a 50-50 beam splitter split that signal into two output mode. And we perform a homodyne detection on each of them. So by introduced pi/2 phase difference between these two local oscillators, then the measured quadrature will be conjugate to each other. So that's why we named that as conjugate homodyne detector. And if we call one of them as X, then the other one we can name that as P. And by calculating the X squared plus P squared, we can estimate the photon number of the input state. So while this structure looks complected, all these beam splitters, balance photodetectors can be packaged in a compact form. And we can use a single laser to generate the two local oscillators for both homodyne detector. And even better, a quantum grade commercial system is available for us to perform this measurement. So now from the definition of the parameter Z, we actually can determine, given an arbitrary input state rho, the probability density of the measurement result Z, which is shown in this formula. And here, the rho nn is the diagonal terms of the density matrix in the photon number basis. And as we can expect it from a phase insensitive detector, the output is insensitive to the phase of the input signal. And that's why we don't really need a phase reference between Alice and Bob. Now, if the input state are number state, and this equation can be further simplified into this form. Okay, and here in this figure, I present the simulation result of the distribution of Z for several different input, from vacuum state up to the photon numbers, a number state with a photon number of 3. And as you can see, these distributions are overlapping with each other. And this suggests that this detection scheme is intrinsically noisy, as we expected from the uncertainty principle. So now let's see how it's performed if we operate it as a threshold detector, as in the case of quantum key distribution. So to do that, we can choose a threshold value for Z, let's say, call that as tau. And whenever the output of the detector Z is larger than this threshold value, we claim the detector has a click. And in this case, we can calculate the detection efficiency of single photon signal by integrate this probability distribution over the range from tau to infinity. And similarly, we can also determine the dark count probability by basically integrate the area under this blue line from tau to infinity. And finally, we can also calculate the ratio between them, and which is an important figure of merit in QKD application. So now the simulation result is shown as here. So the green line is the detection efficiency as a function of the threshold you choose. And the blue line is the dark count probability, and the red line is the ratio between them. Now, as you can see, the performance of the proposed scheme is not as good as conventional single photon detector. So for example, this detector gave us R value about 10 for the useful range, while a state-of-the-art single photon detector can give us R value about 1 million. So while this scheme is not, the performance looks like not as good as conventional detector, it does have a special feature that is we could reconstruct the photon number distribution of the input state through repeated measurement. And that's the case in quantum key distribution when we have a large data size. And specifically, given a large data size, we can determine the distribution of Z from our experimental result. And since this is related to the photon number distribution by this formula, we can apply the, for example, the Bayesian inference method to reconstruct the photon number distribution. And as we have shown in our previous work, so we demonstrate for coherent state and thermal state input, the distribution is constructed from the experimental data matched with the theoretical distribution very well. So now in the rest of my talk, I will consider the asymptotic case, which means we have a large data size, so the photon number distribution arrived at the bulb can be precisely reconstructed.
Bing, before you continue, yes. There's a small question about the introduction.
Mm-hmm.
Erika asks if conjugate homodyne is the same as heterodyne detection. Could you confirm that?
It's kind of depends on which community you are, then there are kind of different definitions. So traditionally, the H-dyne detector is defined for the case when the frequency of the local oscillator is different from the signal, that's called H-dyne. But in the case of CVQKD, we have we also define this conjugate homodyne as H-dyne detection. So I think you're right. In the case of CVQKD, what we studied here is exactly the H-dyne detectors used in CVQKD. And the difference is in CVQKD, we do need to have a phase reference between artist and bulb in order to recover the information encoded on field quadratures. While here we assume such a phase reference is not available, so we can only determine the photon number distributions.
Okay, I think that answers the question.
Okay, thank you. Okay, so now let's move to the QKD protocol. So here I consider efficiency BB84 QKD, which means artist and bulb will choose one basis more often than the other. And in the asymptotic case, they will use the probability to choose the Z basis is approached to 1. So I also assume it's a polarization encoding scheme with a perfect single photon source. And there's no technical imperfections except the channel loss. And I assume the error correction efficiency is 1, and we are working at asymptotic case. So the reason I really try to start with the simplistic case, because we really want to see what's the potential performance before we move into the more practical case. And the diagram shows the basic structure of bulb system. So basically, bulb can use some type of modulator, for example, a variable wave plate, combined with a polarization beam splitter to implement the active basis selection. And bulb also have 2 sets of conjugate homodyne detector, and which allows them to determine the values, the Z0 and Z1. And both of them are analog data. Now, once bulb have this measurement result, bulb can assign the bit values following the conventional rule. For example, if both Z are if one Z is larger than the threshold tau and the other is smaller than threshold tau, then bulb have a definite bit value. And if both of them are less than detection threshold, then we assume it's no detection scheme case, so bulb always throw those data away. And for the case, both of them larger than threshold, we treat them as double-click events. And in this case, random bit value will be assigned. So this rule is a standard in BB84 protocol. And the secure key rate in this case is quite simple. And it's basically R, the Q and E are the gain and the quantum bit error rate, which is defined in conventional QKD. And here, the basis, Z basis will be used to generate the secure key. And so these two terms quantify the cost for error correction and privacy amplification. And in order to determine these two parameters, and this we can use the choosing a threshold for the detector. And once we know the channel loss and the threshold detector, both the gain and the error rate can be easily calculated from the model of our detector. And here I present the simulation result of the secure key rate as a function of distance. And I assume the standard single mode fiber is used for the quantum channel, so the loss will be 0.2 dB per kilometer. And the dashed green line is the secure key rate of the new scheme. And as a comparison, I also plot the secure key rate for a perfect single photon detector with 100% efficiency and no dot count. So now, as you can see, the secure key rate is pretty poor compared with conventional scheme. So how can we improve that? And the main part of my talk will be how can we improve the secure key rate using two spatial features of our detection scheme. So namely, the first one is we know that there are always fundamental detection noise of our detection scheme. And these noise are intrinsic and cannot be controlled by the eavesdropper. So it's reasonable to apply the trusted detected noise model, so which has been widely applied in continuous variable QKD. And the second is because Bob actually can reconstruct the photon number distribution at his end. And this gives us a better way to evaluate the property of the quantum channel and thus bound the Eve's information more tightly. And I will go into the more details. So the approach we are using is as follows. So first, just to facilitate our discussion, we introduced a pair of virtual ideal single photon detector in Bob's system. So of course, these detectors are not available in practice. They are just used for study the security. So the secure key rate is generated from the output of these two real detectors. And we know these two real detectors can be used to reconstruct the photon number distribution after the beam polarization beam splitter. And this information allows us to estimate what the quantum bit error rate will be if we do have a pair of ideal detector here. And once we have this quantum bit error rate being estimated, we can use that information to provide a more tight up bound on Eve's information. And that is a basic approach we are using here. So before I jump into more details, let's first lay out the secure key rate, in this case, under reverse reconciliation. So the reverse reconciliation means during the error correction stage, Bob will keep his shifted key, and Bob will send some classical information to Alice, and let Alice to correct her shifted key. And we also assume the syndrome information is transmitted during this stage are encoded by encrypted by one-time pad with pre-shared key. And in the secure key formula, the last term, that's quantify the cost for error correction, and that is the standard in our standard security analysis. And the other three terms, so the Q11 is the gain from the case when artists send out one photon and one photon arrives at bulb. Note, even a photon arrives at bulb, that means bulb can detect that photon because the detection efficiency of bulb detector is not perfect. But we assume only these terms can contribute to a secret key. And we also use the bit error rate for these cases to upbound if information. But the E11 we used is not from the real detector, but from the virtual detector. And so the argument is like this. So if we do have perfect detector, the E11 is the right parameter to use to quantify if the information on the output of this virtual detector. And because this real detector will introduce additional noise, which cannot be controlled by the eavesdropper. So if information on this output of this real detector will be less than her information than this. So it's always safe to use E11 from virtual detector to upbound if information. And finally, we also have a Q10 term in this secret read formula. And this is the gain from the case where artists send out one photon, but vacuum state arrived at Bob's detector. And in this case, both neither artists or Eve can predict Bob's detector output. It's totally random. So this term is added in to compensate the cost for the error correction. And the reason we can add these terms in is because we are using a reverse reconciliation scheme in our protocol. And so now, once we have this secure key formula, the question is how can we determine all the parameters from the experimental result of our real detector? And to get that, let's first to see how Bob can determine the channel transformations from using his conjugate homodyne detector. Now, without loss of generality, I assume artists send out H photons and Bob perform measurement in HV basis. And for the other cases, it can be studied similarly. So now the channel transformation is defined as the probability that N0 H photons arrived and N1 V polarized photon output from the channel, given artists send in M H polarized photons. And this is completely quantifies this channel under this model. And more precisely, from the detector output of these two conjugate homodyne detector, Bob can reconstruct the photon number distribution, and thus gives us directly the channel transformations that C and 0 and 1 given the input is one photon. So because we are considering the case, artists use a perfect single photon source. And the parameters we are interested in is given one photon input, what's the probability 0 photon arrived at bulb, or 1 H photon arrived at bulb, or 1 V photon arrived at bulb. And with these three parameters, we can evaluate the bit error rate from the virtual detector. So now let's put everything together. So from the detector outputs of the real two detectors, Bob can generate a raw case. And Bob can also evaluate the channel transformation Cn0 and 1 given one photon input. And on the other side, this is the security rate. And although gain and bit error rate can be determined from raw key directly. And the terms like Q10, that is again, when Ali sent out one photon and 0 photon arrived at Bob, can be calculated by the product of the channel transformations. That's given one photon input by Alice, what's the probability 0 photon arrived at Bob, and the times the detector response, which is given 0 photon arrived at Bob, what's the probability Bob will have a detection event. And this detector response can be fully determined just from one single parameter, the threshold for the detection. And the other parameters can be determined similarly. And especially the bit error rate for the 1-1 case from the virtual detector can be easily calculated from the ratio of these two terms. The first term is given one H photon sent in the channel, what's the probability one H photon output from the channel. And this two term is basically quantify what's the probability given one photon in and one photon out, regardless its polarization. And this is exactly the expected bit error rate if we have a perfect pair of perfect single photon detector. So now given those parameters, we can calculate our security rate. And the security rate is shown in these figures. And as you can see, so the ED here is the polarization misalignment due to the channel. So which is basically the probability when Bob receive one photon, what's the probability that the received photon go to the incorrect detector. And as you can see, the security rate is much improved than the previous case. So although it's still below than that of a perfect single photon detector, but it can give us a decent security rate at over short distance. And especially when we consider the optical homodyne detector could be operated at a much faster speed. So we might close this gap if we calculate security rate in terms of bits per second. Now, so from here, looks like if we have a perfect single photon source, then we could have a reasonable key rate at short distance. But now, how about the practical photon source? So for the rest of my talk, I will just present some very preliminary unpublished result on this line of research. So the first source I consider is a non-ideal single photon source, which generates vacuum state with certain probability and single photon state with some probability. But I assume it never generates multiphoton pulses. And such single photon source has been applied in QKD, for example, in a recent work from Thomas Jenneweis group at Waterloo. And this, the security of this this case is very easy to analyze. So because this non-ideal single photon source can be modeled as a perfect single photon source followed by a beam splitter with a transmittance equals to S1, that's a single photon probability. And we can move this beam splitter outside of Ali's lab and treat that as part of the channel. So when we do that, we will not awaken the security of the protocol. And this is the last case is basically we go back to the case with a perfect single photon source, except we need to replace the channel transmittance eta by S1 times eta. So we can basically apply the same security key formula for this case. And these are the simulation results for the case where S1 equal to 1, that's perfect single photon source, or 0.5 or 0.2. And as you can see from here, if we want to have reasonable key rate, we do need a pretty good single photon source, means with a good probability of generate single photons. Now let's move to the phase randomized weak coherent source, which has been widely applied in BB84 QKD, and especially when combined with the decoy state idea, the performance can be greatly improved. And here I consider the infinity decoy state protocol. Now, the decoy state and the synchronous state essentially are the same, except they have different average photon numbers. And the basic idea of a decoy state is by transmitting coherent state with different intensities, Alice and Bob could have a better evaluation of the channel property. And this allows them to bound Eve's information more precisely. Now, for each transmission, Alice will randomly prepare either a signal state with average photon of mu or one of the decoy state. And the measurement result of the decoy state will be used to determine the channel transmittance. Channel transformations. That's the probability given mh photon input, and you have N0 H photon and N1 V photon output. And the signal state is used for, to generate a secret key. So now let's into more details about that. Because we are really using weak coherent state rather than number state, so the channel transformation we recovered from experimentally are really for the coherent state input. That means given a weak coherent state with average photon number of mu I, what's the probability you have N0 H photon and N1 V photon output? But what we really need is the transformation of a number state. So given an M state input, what's this probability? Because these are used for estimate Eve's information. And fortunately, because we are using applied the decoy state, these two transformation functions are correlated by the following linear equations, where the S is basically the Poissonian number distribution of the coherent state. And given we have a large number of decoy state, then all these terms for the transformation of a number state can be determined from that of the coherent state. And that's the basic idea of the decoy state protocol in this case. So now let's look at the secure key rate. It's similar as before, except now we have put a mu on each terms. And this represents that we are using weak coherent state with average photon number of mu to generate a secure key. And another thing you can notice, like previously we only have vacuum state arrived at the term corresponding to vacuum state arrived at Bob. So now we add in more terms. So these terms are quantified again when we have same photon number arrive at the two detector at Bob. And of course, in those cases, you cannot predict Bob's detection result. So for the same argument for the vacuum state, we can add them in to compensate the cost for error correction. And all these terms can be determined from the channel transformation function and the detector response function. And except we also need to add the probability artists transmit a certain photon number in front of rod. And given this formula, the secure key rate is shown in this figure. So unfortunately, the secure key rate is pretty low even at very short distance. And this is kind of disappointing. Like if we use the standard decoy state protocol, and it looks like we won't be have a efficiency for this QKD. But this may not be the end of the story, because so far we have assumed secure key can only be generated from the case when artists send one photon and one photon arrived at the bulb. But we should treat more carefully about those multiphoton cases. And here, let's just start for the case when bulb artists send out 2 photons. Now, in this case, under normal condition, the output channel could be vacuum state or 1 photon state or 2 photon state. And previously, we just throw these 2 terms away because we treat them are not secure. However, there are 2 observations we can make here. First, given Eve knows the photon number arrived at Bob's detector, the N0 and N1, but Eve still cannot predict Bob's measurement result with certainty. And this is because the charged noise introduced by Bob's detector. So Eve's uncertainty about Bob's key could be quantified by this function, where the BR quantifies the bit error rate when Eve tried to estimate Bob's measurement result or Bob's bit value, given she knows the N0 and N1 hit on Bob's 2 detectors. And the second,
I just want to say that we are running a bit out of time. So you should think about going to the conclusion.
Okay, I will go to the conclusion. Okay, sorry for that. So the second idea is really from William Premata and Charles List at NUS, where they, a similar protocol, they shows like for the case when artists send out 2 photons and Bob received 2 photons, you still could generate secure key. So I won't go to the details of that, just show some hand-waving result without giving the security proof. So if we consider those 2 contributions from those 2 terms, then the secure key could be still quite reasonable. And this basically gave us some hope, like to make this protocol works even with a weak current state. And in summary, we proposed a protocol to implement BB84 using conjugate homodyne detector, and we improved the security analysis based on 2 features. One, the detector noise is trusted, and the second, Bob had the ability to reconstruct a photon number distribution. And this give may inherent the advantage of coherent detection without requiring a phase reference, and might be useful for short distance application. And thanks for our founding agent, and you can find more details in these 2 papers. And thank you for your attention.
Yeah. Thanks a lot, Bing, for this nice presentation and very clear. There are no questions currently in the chat, but I'm sure people have questions, so invite them to ask them. Maybe I can start the discussion maybe with a question of my own. So you talked about your proposal as having an advantage for a short distance, having relatively good key rate for short distance, and also having the advantage of having higher repetition rates than discrete-variable threshold detectors. What would be the kind of range of distance where you could say that this approach would be would give higher key rates than usual discrete-variable QKD, if you put everything together?
I would say that's probably within the range of 20 kilometers or something like that. The reason is the scaling of the key rate over distance of this protocol is poor compared with the case when you implement the BB84 with standard single photon detectors. And so that's the reason I think for distance probably about 20 or 30 kilometers, then you will the key rate of this new scheme will be so low compared with the existing scheme.
Okay, I see. Thank you. And so we did the comparison with a normal discrete variable QKD, but how would you compare this method to CVQ QKD protocols, where you do where they do a modulation of coherent states and then usual coherent detection? What would be the advantages of this protocol compared to usual CV or discrete modulated CV QKD?
Oh, that's a very good question. And the CVQKD actually have all the advantages of what I mentioned above, like the potentially high speed and insensitive to broadband noise, because the CVQKD uses the same optical homodyne detection. I think one advantage of this scheme is that we don't need to establish a phase reference between Alice and Bob. And that makes this its implementation simplified. And in terms of secure key rate, I would expect the CVQKD with the conventional CVQKD scheme will have a better secure key rate than this scheme we proposed.
Okay, thank you. Yes, I don't see any other questions. Maybe a last one, and then maybe we can conclude. What would be the main experimental challenges? Oh, we have a question from the public, from the audience. So the question is from Emilien Lavie. Would it be possible to consider the real number value Bob gets from a detector as outcomes instead of only the sign, positive or negative? How would it affect the security analysis?
Sorry, I didn't quite catch that. Could you repeat the question again?
The question is, would it be possible to use the real value, I assume the XNP quadratures, that Bob gets from the detectors as outcome instead of only the binning, the sign that you did, to have more information or more key?
Yeah, I think that's a very good question. Yeah, I haven't thought that too much. Like in this case, that's why that also depends on your encoding scheme, right? So right now, like in BB84, we only encode 1 bit of information at Alice end. And although we have like continuous output, analog output from the detector, how to retract all this information optimally? I think that's a good question. So right now, so in the paper I mentioned, I studied two most simple scheme. One is what I present here. So basically, we treat the two detectors independently, and each of them will have a threshold and convert that real value into binary value independently, and then apply the rule I mentioned to generate the key. So another scheme I have been I considered in the paper is we could just compare the output Z0 and Z1 directly, compare these two real values, and it depends on which one is larger, then we determine which detector click, like kind of perform this jointly detection using the two set of detector. And in that case, you actually have a deterministic result because in principle, if you have a high enough resolution of your AD converter, then the probability Z0 equal to Z1 is approached to 0. So you always have a detection result, and Bob can assign to either bit 0 or bit 1 to each measurement. But in that case, it also has a higher bit error rate. And I compared these two results, and it turned out for the case I have been studying, the independent detector mode performs better than the other, which I call the differential detection mode. But there could be other ways which maybe allows you to recover all this information more efficiently from the pair of two real values. But I haven't thought that too much. But that's a great question.
It was. Do you also have a question from Anton Tosheshkin that I'm going to unmute?
Yes, thank you very much for the very interesting proposal. My question is, if I understood correctly, you assume that the channel transformation is constant. This allows you to estimate the photon number distribution. Does it mean that you essentially assume that the attack is collective, not coherent? And it seems that this is a crucial assumption, or no?
I think potentially, yeah. So because if we consider, so far I have been considered the asymptotic case, right? So even the channel may be fluctuated, it could be time variant, but if we have enough of data site transformations, and and if we perform certain randomized process on those data, we could still recover equivalent channel transmittance for this group of transmission. So in that sense, I think it could be so. Even for the fluctuating channel, it still can be handled with this scheme.
And not just fluctuating, but which is varying in a completely arbitrary way due to Eve's actions. And can your method work also in this case?
I think it still works because this similar as in continuous variable QKD, we need to evaluate the channel transmittance and the excess noise from Eve. So that's basically from the channel. And in that case, Eve, of course, can manipulate the channel transmittance or introduce noise arbitrarily in what she preferred. But given us have enough data, we still can estimate equivalent channel parameters for the period when we conducted the QKD transmission. And I think that is a similar in this case. But of course, now we have much more parameters to be estimated. Like as I show here, we have the channel transmissions C given 1 photon or m photon input, N0 and 1 photon arrived at Bob. So that means in the real protocol, that will be it will be more complicated compared with the CB-QKD case because we have more parameters to be quantified.
Great. Thank you very much. It's very interesting.
Thank you for your question.
Okay, in that case, the session is drawing to a close. Let's thank the speaker, Professor Bing Shi, again. And let's also thank the organizers who are working in the background. You don't see them, but I see them working to make the conference run. The speaker will be available in Meet the Speaker area if you have further questions. And we'll be back tomorrow for the next day of the conference with the poster session starting at 11 a.m. and the first contributed talk, so invited talk at 1:15 p.m. Thank you.
Thank you.